so what we do is we make sure before we turn it on, of course, that there's nobody in the tunnel, because that would not be good. It's like, don't get in your microwave before you turn it on. That would not be good. All right? So don't get in the tunnel before you turn it on. But as long as that's the case, it's perfectly safe. All right? There was some thoughts that when we turn this on, it might create a black hole, and that black hole would swallow up the Earth. In fact, if you go to YouTube and type LHC, black hole that swallows up the Earth, you'll get a nice little video that someone made of the LHC starting and turning on and creating a black hole, and here it is beginning to swallow up the Earth. All right? Well, that can't really happen, and I'll tell you why. Because everything we do in the LHC is already being done in nature. In fact, right here, right, you guys have this cosmic ray detector. Some of you are working on this. This detects particles from outer space. In outer space, there are protons moving nearly the speed of light. And they hit our atmosphere, and they do something called shower. They create new particles, and that thing can see those new particles. In fact, here's a picture of what a cosmic ray shower might look like. A particle from outer space, a proton, hits the atmosphere and creates a whole bunch of particles. And down here in Kingfisher, Oklahoma, is a cosmic ray detector that's detecting those particles. So everything we do in the LHC is already done by nature when particles collide in the atmosphere. If nature could create black holes that swallowed up the Earth, it would already have done it when particles hit the atmosphere. The only difference is we're doing it in a controlled way so we can build a big detector and see what happens. It's hard to build a huge detector that covers every square inch of the atmosphere above the Earth to see where these things hit, and they hit all over. So nothing that we're doing is new. If there was a danger in it, we would have already seen that danger because nature does the same kind of things all the time. We just do it in a controlled way. So this has kind of made me laugh when people thought this might create a black hole. In fact, somebody even had a lawsuit to try to stop the LHC from turning on because they were afraid that they'd create a black hole and swallow up the Earth. But can't do that because it's already been done. We're not doing anything that nature doesn't do anyway. All right? And actually, if we're lucky, we would create a black hole because we'd be actually able to see it. It's what we call a microscopic black hole. It would not swallow up the Earth. It would decay away. And I'll show you a picture of what it would look like if we actually created one later on. Because we can run simulations on the computer of what we would expect to happen if we create certain particles like black holes, and we know what they'd look like, and they wouldn't swallow up the Earth. All right, so the other question is antimatter dangerous? Did any of you see this movie, Angels and Demons? All right, so in the first scene of Angels and Demons, or the whole premise of Angels and Demons is that some really bad guy is going to get some antimatter, and antimatter will combine with matter to create a bomb that will explode and destroy the Vatican or something like that. All right, I didn't think the movie was that good. But anyway, here's Tom Hanks. He starred in the movie. Here's Ron Howard, who's the director of the movie. And this is a picture of the movie set. And the first scene in the movie takes place at CERN, supposedly. And the idea is they're going to steal this antimatter. All right? So this is what the movie world looks like. You got Tom Hanks, you got Ron Howard, you got a set that looks like the control room. Here's what the real world looks like. There's really Tom Hanks at the real collider. He went there to try to see what was going on. This guy right here is named Rusty Boyd. He's actually an engineer who works for the University of Oklahoma. And since we're doing work in Geneva, he lives in Geneva, but he gets paid and he works. He's an Oklahoman. So there's Tom Hanks meeting an Oklahoman at CERN, Rusty. And then here's what the real control room looks like. So you notice it's kind of similar. There's lots of computers, but the lighting is always much cooler in the movie world than in the real world. In the movie world, they have cool... And notice the other thing. In the movie world, scientists always wear white coats. But in the real world, scientists never wear white coats, at least not physicists. So that's how you know it's the movie world, because scientists are wearing white coats. Now, I think this guy's French because he's wearing some kind of weird vest. But, that's not a white coat. It's just a weird guy, French guy wearing a vest or something. I don't know. All right. So anyway, the movie said that antimatter was dangerous. And the answer is it? And the answer is, well, if you could get enough of it. But and we actually create antimatter in our labs. It's really true that CERN creates antimatter. But the amount that we have created over the last 40 years is, about the size of a pinhead maybe. It's very, very little, and it would never do anything like the movie says. So the movie takes a real idea, but it kind of exaggerates it, which is what movies tend to do, right? So anyway, that's cool. It's a cool place to work. You have people like Tom Hanks come through. You have a lot of high-tech stuff. You got, Oklahoma engineers. It's kind of fun. All right, so how do you accelerate protons? Well, protons are positively charged. What do you know about charged particles? Anything? Their charge can change. Okay, that's actually true. A proton will always be positive, but you can actually do things. All right. What happens if a positive charge is brought near a negative charge? Are they attracted or repelled? Okay. Attracted or repelled? Attracted, right? Because unlike charges are attracted to each other. And like charges are repelled, right? All right. So you can accelerate particles. This is kind of math if you've had physics. We won't worry about it. You can accelerate particles with other charged particles or with electric fields, and you can turn particles with magnetic fields. So the short answer, which is what we say today, is you accelerate protons and you steer protons with electric and magnetic fields. So we have huge magnets and huge electrical, a huge energy bill. The electrical bill for CERN is really big because we're using electricity and magnetism to do what we need to do. All right, so let's ask the question, we've been doing this kind of research at least for 40 years. What have we learned? So let me ask you, if you were to take a beaker of water and look at it with a microscope, what would you see? You'd see something called H2O, which is a water molecule. So everything is made of molecules. It's the molecules that actually give things their properties. Water feels wet because of a water molecule. Tables feel solid because of table molecules. And the things that you feel and touch have their properties because of the molecules they're made of. But that's not the whole story. What are molecules made of? Atoms, right? So that's what H2O means. It means 2 hydrogen and 1 oxygen. So every atom, every molecule is made of an atom. And what's at the center of every atom? We already said that. Nucleus, which is what Rutherford discovered. And notice the nucleus is about 10 to the minus 14th meters compared to 10 to the minus 10th for the atom. That's like the baseball and a lot of kingfisher. So the nucleus is really, really small compared to the whole atom. What is the nucleus made of? You guys know that. Yep. Well, the nucleus is neutrons and protons. These things out here are electrons, right? So neutrons and protons. And so if you lived in the 1960s, did any of you guys live in the 1960s? Just checking. Well, some of the older people in the back. Yeah, I know. Yeah. All right. If you lived in the 1960s, we knew that neutrons and protons, that the nucleus was made of neutrons and protons, but we didn't know what neutrons and protons were made of. So somebody at Stanford created this experiment. They put a bunch of protons right here, and they fired a beam of electrons into the protons. There's a person to give you some idea of the size of this thing. And the same way Rutherford fired alpha particles into a gold foil, by firing electrons at protons and watching how they scattered into these detectors, we were able to see that the proton had things inside of it. So just like Rutherford shot alpha particles on gold foil, and the way it scattered, he got to see that there was something inside the nucleus, we did the same thing. We shot electrons on protons, and the way the electrons scattered, we saw that there was something inside the protons. So inside every neutron and proton, there are 3 things that we call quarks. And one of the goals is to try to determine if quarks are made of something, and so far we don't know. We just know that there are quarks and that every neutron and proton has 3 of those. So if somebody asks you, what's the smallest particles of matter in the universe, the answer as far as we know are these things called quarks. And every neutron and proton is made of quarks, and every nucleus is made of neutrons and protons, and every atom is made of a nucleus plus electrons, et cetera, et cetera. So that's kind of the answer to the very first question. It's not the total answer, but it's much of the answer. Right? So how big is a quark? Well, the difference in size between you and a quark. So here's my picture of a quark. And, a quark is small and you're much bigger than a quark. But what's the ratio? How small is a quark compared to you? Well, if you compare your size to the distance to the farthest galaxy you can see with your eye. So the difference between you and the farthest galaxy you can see with your eye is the same as the difference between you and a quark.